Hi, hello.
Hello, Brian.
Hello.
Hello, how are you guys tonight?
Good. How are you?
I'm doing fine. I'm doing fine. Are you feeling much better about the midterm 1 material? You moved on to midterm 2 material, right? You guys started learning about alkynes, I think? Like triple bonds?
Yeah,
Uh-huh.
we started that today.
Let's see. Let's get
Recording in progress.
yeah. The alkyne stuff is very similar to the alkene stuff. It's basically the alkene stuff times 2, like the reactions, but you basically do it 2 times because you have another bond to work with. So before we get started, I want to go over the differences between reductive and oxidative ozonolysis. But for helix's 118B class, you guys just have to worry about the reductive ozonolysis. So, for example, let's say we have this alkene right here. All right, and for helix's 118B class, the two reagents that you're going to see are the first step is O3, second step is going to be dimethyl sulfide. So CH3 to sulfur, like that. How would you guys predict the product here? Like, what would you guys do to predict the products from this reaction here?
Cut it and replace the double bonds with O's.
Yep, cut the alkenes in half, like that, and put O's in the middle, like that, to get the answer from this reductive ozonolysis. Right, first step is O3. Second step, when you see this dimethyl sulfide, that is a reducing agent. So the answer will be as is after we cut it, right? We are going to stop at either the aldehyde or the ketone. So the way that I draw my product is going to be like this. Right. And
Bro, actually, dimethyl sulfide is a oxygen trapper. In O3, it traps one oxygen and other two oxygen put on the alkenes.
oxidant trapper?
Yeah, oxygen trapper.
Trapper. Okay. Yeah, because I see here in a different source it says it's a reducing agent, so we might be looking at different sources. For your material, you could think of this as the oxidant trapper, but if you like instead react this with the second step of an oxidizing agent like hydrogen peroxide instead, that's when you do the oxidative ozonolysis, where instead of stopping at the aldehyde, you go all the way to the carboxylic acid. So when you use an oxidizing agent like hydrogen peroxide instead of stopping at the aldehyde, those aldehydes will go all the way to the carboxylic acid. Right. So all these aldehydes here are being converted to carboxylic acid if we use a oxidizing agent like hydrogen peroxide. Right. What does your source say about H2O2? Like, is it what kind of reagent is that? Right. But for helix's 118B class at UC Davis, don't worry about this reaction here. It's just the first reaction with the dimethyl sulfide, where to get the final answer, just cut the double bonds in half and put oxygens in the middle, like that, right, to get the final product there. And you can leave your answer as this right here. You don't have to straighten it out or make it neater, because your TA, when they grade it, they will be able to understand that and grade that. Right. Okay. Any questions on this reaction? Okay. So here is the table of reactions for chapter 11 and 12. The reagents for them, the regioselectivity and stereoselectivity. Make sure to know this for the conceptual question for sure, and also be able to explain why, because those explanation problems where you like he asks you to write like a paragraph or something explaining why it's anti-addition versus in-addition, that's testing your knowledge of the mechanism, like the step-by-step mechanism, right? And the ones I start here in yellow are the ones that that you would have to know for sure the mechanism for, right? The other ones is less less likely to show up as a mechanism problem, right? Here's a note card that I made for 118B helix like some quarters ago, where it goes over like each reaction's mechanism, but it's like very simple because I didn't do like the hydride shift. Like if you see here, isomerization, once I form this carbocation, we just get what shift for the double bond. There's no hydride shift. But keep in mind that whenever you form a carbocation intermediate anywhere in any sort of mechanism, always stop and look out for any rearrangement, like a hydride shift or methyl shift, to see if you could make the more stable carbocation due to more hyperconjugation or resonance. Right. Okay, mass spectrometry notes, conceptual question, multiple choice question on the exam. And then here's the winter 23 practice midterms. So Layla, let's go check your answers here. Winter 2023 midterm 1, section A. Okay, so we did this part. Alkene reaction with Br2 and water. Br attack once breaking ammonium, then H2 attack the more subside, breaking it up. Yeah. Yeah. So your answer here is correct. And the explanation for the mechanism is also correct. The water, which will eventually become the OH, attacks the more subside, Markovnikov addition. The bromine is on the anti-Mark side, the less sub addition. And since this is the only chiral center we have, and that's the one that changes, we could put that plus minus symbol to show the plus enantiomer version of it as well. Do you guys want to go over the mechanism just for extra practice, or you guys want to move on to like the next problem? So for the next one here, we have HBr with peroxide, ROOR. This bond right here between the two oxygen atoms is very weak and unstable. And when you see that weak, unstable peroxide bond, think of having a radical somewhere in the mechanism, which will lead to an anti-Mark reaction, right? Where the nucleophile will attack the less subside. So this is our anti-Mark carbon, aka the less sub carbon, right? Whereas this as our Markovnikov carbon, because that's the more sub carbon. Yeah, Rehan?
This reaction is called Karsh effect, right?
Sorry, what was that? Charge effect?
Karsh effect.
Charge effect?
Karsh effect.
Charge. So can you type that in the Zoom chat? I see.
Okay.
Yeah. Karsh effect. I have not heard that before. Let me see what that is. Actually.
We call it Karsh effect.
Karsh effect. Let me see. Karsh effect, also called the peroxide effect or anti-Markovnikov addition, is a phenomenon where the addition of hydrogen bromide, HBr, to an unsymmetrical alkene occurs in the opposite way than predicted by Markovnikov's rule when a peroxide is present. Yeah, so that is also known as Karsh effect, aka the peroxide effect, which is this peroxide bond, or anti-Markovnikov addition, right? So another way of it is Karsh effect. Yeah. Right. So since this is the anti-Mark position or the less sub position, we're going to attach bromine on that carbon like that. And I'm not putting wedges or dashes here because that's not a chiral center, right? We only put wedges or dashes on chiral centers. There's two hydrogens here, so that's not a chiral center. Flat bond right there. Right. Okay. So Layla's mechanism problem. We have these reagents, an alcohol, an alkene, reacting with a strong non-nucleophilic acid, sulfuric acid, H2SO4, giving us this ether here. So when you see two competing bases, which is this alcohol here versus this alkene, the alkene will be the stronger base. You're going to choose the alkene to get protonated in the strong acid, right? Because we have strong acid present in the solution. But we have two possible bases, the alcohol, oxygen, or the alkene carbons. The alkene carbons are going to be more basic than the alcohol, so we're going to protonate the alkene. If we want to protonate this alkene right here, what is going to be the intermediate as a result? Like, let's say we protonate this carbon here. What's going to result? What intermediate is going to result? Right.
Carbocation.
Carbocation intermediate, yes. And let's say this is carbon A and this is carbon B. Where would the carbocation be at?
On the tertiary carbon.
On the tertiary carbon, that's right. The more substituted one, because that is the more stable position. Because of what factor? What factor makes that more stable? Like, what factor makes a more substituted carbocation more stable than a less substituted carbocation? There's actually multiple factors, but what factor in this molecule here with no resonance? Starts with H, hyper conjugation, right? A way to think about that is that the orbitals of the R groups here inductively donate electrons into the carbocation, making that carbocation more neutralized, more stable. If you are comparing that with the secondary carbocation, let's say, there's less R groups, less donating groups to donate electrons inductively to that carbocation, making it less stable, less neutralized, right? So the more substituted the carbocation is, the more stable it is due to something called hyperconjugation, right? Once we have this carbocation intermediate here, we stop and we look out for any rearrangement steps that we can do, like a hydride shift or methyl shift. Since it's already in this most stable position, we don't have to worry about any hydride or methyl shifts there. Now, once we have this carbocation, this carbon here is our electrophile, right? Because it is positively charged, it could be attacked by a pair of electrons or a double bond. And the thing that is going to attack it here is like not water or alcohol on like the reagent arrow, but it will be this alcohol here on that reagent, right? Where this oxygen alcohol is our nucleophile. So if I draw out that alcohol out like this with its two pairs of electrons, I'm going to use one of its pairs of electrons to attack that electrophile right there, right? If I star my nucleophile, that oxygen atom, and dot my electrophile, that carbon atom, I'm going to make a new bond between the star and dot, a new bond between the nucleophile and electrophile. So my intermediate here would then be this. This is the oxygen atom, that's the nucleophile, purple star. This is the new bond that is going to be formed between the star and the purple carbon. This purple carbon here is attached to 3 methyl groups, 1, 2, 3. And I'm going to draw that 3 methyl groups out like this, 1, 2, 3. This oxygen right here that attacked that carbon is still attached to this hydrogen atom right there. And I'm going to draw out that hydrogen atom explicitly out with that bond right there. Now, what's missing here? What's missing in this intermediate? Right? I attached every single atom to every single group, but I'm missing one thing here from this intermediate.
Would it be a positive charge on the oxygen?
That's correct. A positive charge on the oxygen, because before it had 2 bonds and 2 pairs of electrons, but now when we used one of its pairs of electrons to make this new bond right here, right, the 2 electrons of that bond came from this pair of electrons. This oxygen now has 3 bonds and 1 pair of electrons. And when we calculate formal charge, oxygen is on the 6th column, but it has 1, 2, 3, 4, 5 electrons to itself. 6 minus 5 is positive 1, giving that oxygen a positive charge of 1. Now, we want to get rid of that positive charge to make it neutral, right? And we see here in the product that that oxygen there does not have a positive charge and does not have this hydrogen here. So what do you guys think is going to happen in the last step of this mechanism?
Remove H plus.
Yes, remove H plus, deprotonate the oxygen using the HSO4 minus conjugate base that we formed in the beginning, right? And when this HSO4 minus here grabs that H, the bond between that H and oxygen right here, those two electrons are going to go onto this oxygen here, giving that oxygen its second pair of electrons and making it neutral again. And we also formed our acid catalyst back. We get our H2SO4 acid catalyst back from this last step. Right. So that is the mechanism. Yeah.
Bro, I have a question.
Yeah.
Why didn't you go H2SO4 directly alcohol with E1 mechanism?
Oh, like why didn't I do E1 mechanism where I protonated the alcohol with H2SO4 and then do E1 mechanism instead?
Yeah.
Yeah, so there's two reasons for that. We have a competition between bases. We have an alcohol, OH as a base, versus an alkene as a base. The alkene is going to be the stronger base, so we're going to protonate the alkene rather than the alcohol. Another reason why we don't do E1 is because we do not have heat. When you see this delta symbol or triangle symbol, that represents temperature or hot conditions, right? And that temperature or hot conditions favors the E1 mechanism. But we don't have heat there, so we're not going to favor E1.
So if you put heat, then it will go E1 mechanism.
It would go do more E1 mechanism, yes.
Okay.
If you had heat there, yeah.
Oh.
And some professors, they're more specific on what the heat is. Like they might specify what temperature is hot. Like I know for Levin's class, right now in this quarter for 8B, she says 180 degrees is hot, 135 degrees is like not hot enough to make E1 favorable. For your class or OChem class, do you just see this delta symbol or are you also given a specific temperature?
No, just delta symbol.
Just delta symbol? Okay, that's good. Yeah, because that's most classes. You just see that delta symbol and you get E1. Right. Same as for Helix's class. Okay, that's good. Any questions on this mechanism?
Yeah, how come it became like a full new bond again? Because it's like 4 carbons now instead of 3 from the other thing.
Oh, for this carbon right here?
Yeah.
Yeah, so that carbon right there is this carbon right here, which only had 3 bonds. 1, 2, 3. And because it only has 3 bonds, it has 6 electrons, right? Two electrons for each. That means that it's missing the octet rule. It's missing 2 electrons. It's not satisfying the octet rule. And because it's missing 2 electrons, there's an empty p orbital right there, giving that carbon a positive charge. That carbon there has a positive 1 charge, because if you calculate the formal charge of that carbon is on the 4th column of the periodic table. But right now, this carbon has 3 electrons to itself, so 4 minus 3 is positive 1, giving that carbon a positive charge, empty p orbital. Oxygen, with its pair of electrons, is attracted to that positive charge, right? Because this is our nucleophile, this is our electrophile. Our nucleophile here is going to attack that carbon using this pair of electrons right here on that oxygen. That pair of electrons, when it attacks that carbon, is the one that makes this new bond right here, right? Because that bond has 2 electrons. Those 2 electrons come from that pair of electrons on oxygen right there. And now this carbon has 4 bonds, right? It gained a bond from this pair of electrons. So that's why this carbon here is now neutral, right? We got rid of that carbocation because it gained a bond. So when we calculate the formal charge again, 4 minus 1, 2, 3, 4 electrons that it has to itself is 0, like that. Right? So that's why this carbon here was able to gain a bond, because of this carbon's electron deficiency. It is missing 2 electrons. It has an empty p orbital. So it wants to accept electrons. It wants to get attacked by a nucleophile, which is this oxygen's pair of electrons here in this reaction.
Okay, thank you so much.
Yeah.
Is there a formal name for this mechanism?
Yeah, the formal name of this mechanism would be hydration of alkene. So it would be this reaction here specifically. But there's two different reagents that you can see with that. You could either have water giving you an alcohol product, or in this case that we just saw, we had alcohol, which would give us an ether product, OR product. And that is, for helix, he calls it halo hydrogen formation. Well, actually, no. We didn't have X2. It's hydration right here. This one. Hydration of alkene. Where we had alkene reacting with H2SO4 strong acid, and we could either have H2O water or ROH. If we have H2O water, our product would be an alcohol somewhere, OH. But if we have ROH, some sort of alcohol, our product is going to be some sort of ether, OR. Right? A way that you can think about it is that we're basically minusing one hydrogen for each substituent. If we use water, minus one hydrogen, OH. If we use alcohol, minus one hydrogen, OR. Right? The way that it was given to you or presented to you in the problem was kind of weird because you're used to seeing water or alcohol on the arrow, on the reagent arrow, right? But in this reaction here, you're given it as a reactant, right? Meaning that it's on the reactive side rather than that arrow side, right? Because you usually see it in this form. That's alkene reacting with H2SO4 and that alcohol right there. But that means the same thing, right? Because we're reacting those two reagents reacted together to get the product. Like that. Yeah. So don't let that trip you up. If Helix decides to scramble things around, like he could have done this instead. Like he could have put the alcohol on the reactant, acid here, and the alkene right here, right? So just think of it as all the reagents and reactants reacting together with the strong acid, and then be careful here. Do not protonate the alcohol because that's less basic than this alkene. This alkene here is more basic than the alcohol, so we're gonna protonate that alkene with the H2SO4 instead, right? So like this, and this right here, they all mean the same thing. It's just presented differently. Right, they will go through the same mechanism here. Okay, so for this synthesis problem here for Wednesday 2023, let's see here. My approach for synthesis problems is that I like to find my similarities and differences between the reactant molecule and the product molecule. I'm going to highlight what is going to stay the same, which is that 6-membered ring right there. Right? And then I'm going to circle the new functional group, which is that carbonyl right there. We did not have that carbonyl before. And we see that we have bromine and the methyl group on the reactant molecule. So if I count the number of carbons for this reactant molecule, I have 1, 2, 3, 4, 5, 6, 7 carbons in the reactant molecule. If I count it on the product molecule, I have 1, 2, 3, 4, 5, 6 carbons on my product molecule. I lost a carbon from my molecule, so I know that I have to use a reaction that will cut a bond to get rid of that carbon. What alkene reaction have you guys learned that cuts a bond in half? And I like to call this reaction the scissors reaction. So that reaction would be called ozonolysis. So let's go backwards here, retrosynthetically. Let's say that this carbon double bond oxygen here came from ozonolysis. So the previous intermediate is going to be this alkene right here, where we're going to do ozonolysis with first step O3, second step dimethyl sulfide, right? Which will cut this double bond in half and put oxygens in the middle like that, right? Where this product here comes from this end of the product, and we do technically have another product, which is that right there, but we don't have to worry about that for the synthesis problem, right? So our intermediate here that came previously is this alkene right here. Okay, so we can say that this alkene right here coming out of the ring came from that methyl group right there. What sequence of reactions can you guys think of that would transform this reactant molecule to this less subalkene right here? I'll give you guys some time to think about this because I think you guys haven't seen this synthesis family yet. The one he posted on Canvas is the 2024 one, I believe. This is the 2023 one, right? And I'll give you guys a hint. All of these reactions here are gonna be 118A. Wait, actually, no. There's a 118B reaction in there. So, yeah. But there's gonna be a lot of 118A reactions to transform this into this with one 118B reaction. Give you guys some time to think about that, and I'll guide you guys through how to think about this if you guys are stuck.
This problem is actually very interesting.
This problem's interesting. Yeah. Are you familiar with like this synthesis type problem where you transform a reactant molecule that give you into a product molecule, like with multiple steps, multiple reactions?
We are given 4 options, so it would be easy for us.
Oh, like a multiple choice
Yeah.
question. Yeah. It's not open ended like this, huh? Yeah. How long is that exam that you're gonna take soon?
3 hours.
3 hours. Oh my gosh. Is it like 5 days from now?
Yeah.
Dang, that's good. Are you feeling ready?
No.
Oh shoot. What is it on? Like OChem? What other subjects?
Other subjects are physics, maths,
Physics,
inorganic
maths,
chemistry, physical
inorganic
chemistry,
chemistry.
organic chemistry.
Oh my god. So it's mostly chemistry, like physical, inorganic, organic chemistry, and then some math in there. Physics
It's equal portion.
Equal
Physics.
portion for it. Yeah, I see.
Yeah.
I see. Dang. What subject do you like the best? Are you more
Organic.
confident with? Organic. Oh my gosh. Yeah.
Organic than physics.
Then physics.
Yeah.
I see. Yeah. Me too. I prefer OChem over physics.
JEE Advanced actually 6 hours exam.
6 hours exam. Any breaks in between?
1 hour break.
1 hour break. Okay, that's good. Lunch break, huh? Probably.
Yeah.
Yeah. Dang. Have you taken any practice exams? Like run through the simulation on the test, like set a timer and everything.
Yeah, we practice
Mhm.
lot at home.
That's good. That's good. And you said there were like 2 types: the main one and the G one.
JEE Mains and JEE Advanced.
Are you taking the main one?
Yeah.
Okay.
First we have to qualify mains now.
Mm.
Then we can give JEE Advanced.
Yeah. Is it the same subject though? Like physics.
same.
Okay.
But the level difference is very tough. Jade mass is very tough.
Dang, I see. Okay. Anyone have an idea on how to transform this reactant to this intermediate? You could either go forward or backward here.
Like, I can think of the BR doing an E2 reaction and making the Hoffman product with the bulky base, but I don't know how the bottom methyl just disappears.
Oh, yeah, so this bottom methyl right here is going to be that alkene right there. We're going to try to make an alkene with this methyl group right there, right? And if you're saying that we're doing LDA, let's say as the first step, Hoffman E2, we're going to have an alkene right here, right, on the ring. And we don't want the alkene inside the ring. We want the alkene outside of the ring. And that alkene outside of the ring is going to come from that methyl group right there. Right. So because we want the alkene on that methyl group, you notice how this pink carbon right here that I'm color coding is that pink carbon right there. We do want to do an E2 reaction with this bromine, but we're going to do a Zaitsev E2 reaction instead to make the alkene connect with this methyl group right here, because we want to like basically crawl our way into that outside portion methyl group, right? We want to first make an alkene inside the ring that touches this pink carbon, and then once we have that, we then can think about what's next, right? So instead of E2, let's do, instead of Hoffman E2, let's do Zaitsev E2 with a small base like NaOH and water. Right. So when we make that more stable alkene, this methyl group here loses its stereochemistry, right? Because it's now flat, planar, sp2 hybridized. Every single group bond here on this carbon is flat and planar, no wedge, no dash, right? Now, you notice how this is the less substituted alkene. We can say that that came from the E2 Hoffman. So we could go backwards and say LDA here, where the pink carbon right here had the bromine leaving group. Let's say good leaving group like bromine. Just like this right here, right? That pink carbon right there. And when we use a bulky strong base like LDA or butoxide, we're going to make the less stable, less substituted alkene right here. What reaction can we do to create a bromine here from this alkene?
Peroxide effect.
Peroxide would be Markovnikov or anti-Markovnikov addition if we do peroxide effect or Karsh effect.
Anti-Markovnikov.
Anti-Markovnikov, right. We see bromine here is on the Markovnikov position, the more substituted position on the alkene. So we don't want to do the peroxide effect. We actually want to do the regular Markovnikov addition, which is going to be HBr, regular HBr with no peroxide, no ROOR.
Yeah.
Right. Yeah. If you did do peroxide effect with HBr and ROR with heat, you would have a bromine at the less sub position. And that's basically going to go backwards to what we started with, right? But with different stereochemistry now. So to summarize, the first reaction we did was E2 Zaitsev. Second reaction we did addition of HX or hydrohalogenation. Third reaction, E2 Hoffman. And then the final step, ozonolysis. 3 reaction synthesis. 1, 2, oh, the 4, yeah. 1, 2, 3, 4. 4 reactions. Okay. Any questions on my thought process behind this synthesis problem here?
I guess just like, how did you figure out to do E2 less sub and then like get the BR on there and then go from there?
Oh, like from this alkene right here, how did I figure out how to go E2 Hoffman to go backwards to this intermediate?
In the first part.
Uh-huh.
E2's 8 step to the addition at first.
Oh, yeah. I know to do E2 stuff because I see that this alkene right here coming out of the ring is coming from this methyl group right here that we have in the reactant. Right, that methyl group became a double bond to make that alkene right there. And if I want to make this alkene right here, I think of the ways that I know that can make alkenes, which is either elimination reaction, like E2 or E1 reaction, or dehydration of alcohol, right? You could have done dehydration of alcohol here too, but that would have been a longer route. So this alkene right here that we have could have came from two reagents actually, right? It could have came from this reagent that we used, or it could have came from this reagent right here, right? Where we have a good leaving group on this carbon versus a good leaving group on that carbon. Both of these reactants here could have made this alkene right here. I decided to use this reactant because it is going to be much more approachable and we could form this from this reactant more easily than this reactant over here, right? Because if you look at the pink carbon right here, that pink carbon that I have been tracking all along in this mechanism or synthesis is this pink carbon right here. And we see that that pink carbon right there is right next to this good leaving group bromine right there. And if I want to make a double bond right there, that's the more sub alkene, the Markovnikov or Zaitsev alkene, right? So if I want to do the Zaitsev alkene, then I gotta use a small base, right? So another way you can think about it is that I want to go towards this methyl group here to make an alkene there. And if I want to go towards this methyl group, I want to make an alkene that touches that pink carbon that I've been tracking, right? To do that, I've got to do E2 Zaitsev. The reason why I don't do E2 Hoffman is because I would have made the less sub alkene, which is here, which is farther away than this pink carbon, right? It does not touch this pink carbon. This E2 Hoffman alkene does not touch that pink carbon, which gets further away from this desired intermediate we want in the synthesis.
Okay, that makes more sense. Thank you.
Yeah. Let me give you a similar synthesis problem for you guys to try out. And then we'll move on to the next questions, the next 3 questions that you have. Right. I'll create a similar one for you guys here. Okay. Try this synthesis problem out. And then I'll give you guys a few minutes to try that, and then we'll see what you guys think about. Oh my god. No double bond here. No double bond in the product. Just that alcohol. Oh wait. Wait, no, don't do this, don't do this. There's a problem here. There's a big problem here. do here? Let's do this. Let me see. This will create that, and then after we have formed that, we create this. And after we create that, we go straight to there. Okay, yeah. This one here should be doable now. Yeah. Okay, try this one here. The product will not have a stereocenter because in the synthesis, we're gonna lose that wedge, and then when we do the other reaction, it could go both ways. It could make a wedge or dash. So product will have no stereocenter here, right? That isopropyl wedge will lose its stereochemistry somewhere in the intermediate.
I think you should put the alcohol on the tertiary carbon in product.
That's gonna be a different synthesis problem if I put alcohol on this tertiary carbon, which we can take a look at that after this problem here.
Yeah.
But the way that I'm designing the synthesis problem here is that I'm putting the alcohol on this carbon because I want them to use a specific reaction, right? Try to think of a reaction that would add alcohol on the less subcarbon. That's the reaction I want them to use. But if you did put alcohol on the more sub position, they will have to use a different reaction. But we'll take a look at that. And you guys can either think about this retrosynthetically, like going backwards here. Like if you notice this alcohol is on the less subcarbon, think about what reaction could have made the alcohol and added that on the less sub antimark position, and then go backwards from there. And then when you get stuck, try going forward and then meet in the middle somehow. Does anyone have an idea of what's going to go on here? Like either backwards or forward?
Proceed with even, I think. Even.
From here?
Yeah.
Yeah,
when
so
you form the carbocation, it will rearrange.
HBr. Let's say we use HBr. The bromine, is it going to attach at carbon A, B, C, or D?
I think C carbon.
So the carbocation will be formed at carbon C, but when we, let's say, have that carbocation right there, what do we have to do once we have this carbocation intermediate right here? Like what step do we look out for? This step is the step that we have to watch out for, especially once we have this carbocation intermediate right here. Right. We gotta look out for any rearrangement steps like a hydride shift or methyl shift. So this hydrogen right here on the left side that's invisible can do a hydride shift right there, forming a carbocation right here. Right. And then once we have that most stable carbocation, Br minus is going to attack that carbon, attaching the bromine and carbon B instead because of that hydride shift, because of that carbocation rearrangement. So when I proceed with HBr, I'm going to have bromine on that carbon B right there, which is why we lost the stereochemistry of this tert-butyl group, because it came from a carbocation intermediate, a flat planar carbon. Right. Okay, so this is, let's say this is the first reaction. Do you guys want to proceed with this or go backwards here? We could go either way. There's different strategies there.
Maybe proceed.
Okay, so let's proceed with this halocane. What reaction would you want to do from this halocane here? Yeah, let's go straight here. So when we get stuck, I recommend thinking about it backwards, retrosynthetically. We see alcohol here is on the less subcarbon if there was a double bond right there. What reaction do you guys know that adds alcohol on the antimark position? It's a long name. It starts with a H.
Hydroboration oxidation.
Yep, hydroboration oxidation. So let's say we go backwards here, where our alkene was right here, and we added alcohol on the less subcarbon, the antimark carbon. To do that, we gotta do hydroboration oxidation, where the first step is BH3, THF. Second step is hydrogen peroxide, H2O2, NaOH, water. So that's going backwards. Now, we started with going forward, and then we went backwards. Now let's try to meet in the middle. What reaction or what reagent can we add here that would create this less subalkene from this haloalkane right here?
Do E2 reaction, then HBO. Hydroboration oxidation.
Yes, hydroboration oxidation here. And what
But-
kind of E2 reaction do we want to do here? Do we want to do Zaitsev or Hoffman E2?
Hoffman. I think.
Hoffman, yes. And to do that, we could either use LDA or tert butoxide, because we want to make the less substituted alkene, less stable alkene. We don't want the alkene here. We don't want the alkene on the more sub position, right? Because if we had it here and we did hydroboration oxidation, our alcohol would be here instead. But we don't want that, right? That's not our product. Right. So the three reactions we did here was hydrohalogenation, E2 Hoffman, then hydroboration oxidation. Right. I'm going to give you guys another step here because I've seen Helix done this on his previous exams for 118B. Instead of stopping at that alcohol right there, let's say he stops at this aldehyde right here. Right, there's going to be one more step. Right, because after hydroboration oxidation, we will have that primary alcohol. But there's going to be one last step here to convert that primary alcohol to this aldehyde right here.
Oxidation.
Oxidation, yes. And with
PCC.
Yes, PCC, a weak oxidizing agent like PCC. We don't want to use Jones because Jones would go all the way to the carboxylic acid. If this was a carboxylic acid, then you would want to use Jones, right? So don't forget about the oxidation reactions as well. Right. oxidation. Nice. Okay. I'm just gonna give you guys 2 more synthesis problems to try at home, and when you guys have them, you guys can send me a message on your work, and I'll check them. But I will be having a 119B midterm 1 review session next Monday from 9 to 11 p.m. So we could go over this during that time as well. Or if you guys want to see it sooner, you could send me a message, and I can have a look at it. Right. And these ones here are going to be relatively simple synthesis problems, right? Because this is going to require 2 steps at most, right? So think of these as warm-up baby synthesis problems. And by the midterm 1 review session, I'm going to have more helix style synthesis problems with 3 to 4 steps, right? But think of these as like the warm-up ones. Actually, let me create one more here for you guys to try. This one's just going to be like more involved, this last one here. Let's say we have this, and I want you guys to create this right here. No. Let's do this. What do I want to do here? Ooh, yeah, let's do this one. Wait, hold on. It is coming from there. Okay, we do this, we get that. Then from here, we're gonna go for it's gonna be 1, 2, 3, 4, 5, 6. At least I would say 5 to 7 reactions for this synthesis problem here. The last one. Right? These right here we have 2. The last one we have 5 to 7 steps reactions. Right. Okay. So let me check Layla's other 3 question for the practice midterm. Okay, right here. Which is number 5. Wait. For the number 5 ABC, is that from 1 through 23 section A, Layla? Oh yeah, it is right here. Yeah, I'll find it. Okay, so this is predicted product problems. The first part A, we have this alkene reacting with these set of reagents. And you said this is oxymercuration, demercuration. We add water or alcohol. In this case, we have water to the more subside, Markovnikov side, right? And this is the reducing agent right here, where our more subside is going to be that carbon. And because we have water, we're going to put alcohol right there, right? And it could be a wedge or a dash. Let's choose a wedge, OH. And I'm going to put plus minus right here because it could have been reversed. This alcohol could have been dash, and this metal here could have been wedged, right? So when you put stereochemistry on this carbon, make sure to have 2 flat bonds, 1 wedge bond, and 1 dash bond, right? For your product, you chose the alcohol to be a dash, so make sure to choose one of the bonds to be a wedge. Right. For the next one right here, we have this alkene reacting with HCl. So this one here is going to be a little bit complicated because we have 2 chiral centers here. This chiral center and this chiral center. If we reacted with HCl, it doesn't matter which carbon we form the carbocation or grab the H with, right? Because they're gonna form the same carbocation. Let's say we form a carbocation right here, where this carbon here grabbed that H. Once we form this carbocation, then we look out for any rearrangement steps, like a hydride shift or methyl shift. We could do a hydride shift here, forming the more stable tertiary carbocation, right? Where this carbon here loses its stereochemistry. That methyl is no longer a wedge, it's now a flat bond because this carbon here is now sp2 hybridized, trigonoplanar, flat. Everything is flat, no wedge, no dash. This methyl up here stays untouched, so it stays as a wedge. Once we have our most substituted carbocation, our Cl minus that we got earlier is going to attack that carbocation, and because it's flat, the chlorine could attack on the top side, giving us a wedge chlorine, making the methyl a dash, or it could have attacked on the back side, giving a dash chlorine, making the methyl a wedge. Where we notice that the other methyl group here stays untouched. It stays as a wedged group. We could not use plus minus like you said here, because this plus minus here shows enantiomers, right? And back in 119A, enantiomers are when all chiral centers changes, right? We have 2 chiral centers here, this one and this one. We see that only 1 chiral center changes for both products, which is the one on the bottom, the one that reacts. The untouched one on top does not change at all. So if some chiral centers change and some stay the same, we consider these to be diastereomers, not enantiomers. These would be diastereomers. So we cannot do that plus minus symbol like that here. Right. Okay, so these are our 2 diastereomer products here. For the next problem, we have this alkene reacting with OSO4 as the first step. Second step, reducing agent H2S with water, which when you see that, associate that with dihydroxylation, syn addition of vicinodiol, 2 alcohols adjacent to each other. So we're going to put alcohols on both carbons of the alkene on the same side. And you got them correct. You could either have the alcohols on the wedge, both wedge like this, or you could have had them both dashes. But in this reaction, there is a major and minor product here. What would you guys say is the major product and what would be the minor product? And for what reason, right? What factor determines the major and minor products here? Right. Would you guys say A is the major product or B?
I think B.
Yeah, and for what reason?
I think steric hindrance.
Yes. Major and minor. For Helix's key, you could omit this. It's okay to not include that because that's a minor product, but he won't take points off if you include this minor product, right? But you do have to have this major product in here, right? Where the alcohols are on the dash and the methyl group here is on the wedge, going away from each other, having less steric hindrance, more stable, major product here. Okay. Yeah. Okay. Any questions on these predicted product problems?
If it was like reverse and the method was dash, then would the other one be major since it should be like the opposite, or is it?
Mm-hmm. Yeah, if it was reversed and this method here was a dash, then this would be major instead, right?
Oh.
Because the groups here are facing away from each other, less steric hindrance, major. If this was a dash, then every group would face on the same side, the back side, and that's not good, right? That's gonna bump into each other, aka steric hindrance, and that's not good. We don't want that. It's gonna become less stable. Minor. Yeah. Okay. So going back to the synthesis problems that I gave you guys here, I'll give you guys a hint for these first two, because Helix, I don't think he'll give this as the first step. The first step for both these is for a 118A reaction, right? And then the second step is a 118B reaction. So I'm telling you guys that these two synthesis problems here, it's two reactions. First step is a 118A reaction. Second step is a 118B reaction. But for this last one that I just created for you guys, it's gonna have 5 to 7 steps. Mostly 118B reactions. Okay. Yes, and I will be having a review session this upcoming Monday. What do you guys want to go over mostly? Like synthesis problems, mechanism, predicted product, everything in general, nomenclature? Because these office hours, I haven't been going over nomenclature, spectrometry, spectroscopy, or conceptual questions that much. I've been going over a lot of reactions, mechanism, synthesis, problems.
Could we go over the next one in mass spec and stuff?
Mass spec? Yeah. We could go over mass spec conceptual questions. Next one.
In the beginning, you mentioned that we might have to be able to explain why something is sen and why something's anti.
Yeah, let me give you an example of that like type of problem here. So the why something is sin versus why something is anti is more for stereoselectivity, right? But he could ask something about regioselectivity, just like this 7th question here, this explanation problem right here. Right, briefly explain why the bromination of alkene will result in different products depending on the choice of solvent, CCl4 versus CH3OH. Right, so he's gonna describe a reaction in words, and you're gonna have to know like what reaction he's talking about, and know the regioselectivity or stereoselectivity depending on what he's asking about, and explain it. Right. I think the other midterm here has the stereoselectivity part, which is this one. Yes, for this midterm here, it's talking about stereoselectivity. Briefly explain why the addition of Br2 is selective for the anti-addition product, whereas addition of HBr is unselective. Right, when you add HBr, it's not anti or syn, it's random. And you have to explain why, like what intermediate makes it like that, and what mechanism, backside attack, carbocation intermediate. Use those terms in the explanation question.
Is there like a general rule for that, or do you just have to remember this like case by case, mechanism by mechanism?
So it's not best to memorize it, it's best to understand the mechanism behind it, right? If you want to memorize it, then you could put this chart in your note card and it will show you all the regioselectivity and stereoselectivity of the reactions, but it's not good for explanation and understanding conceptual questions. Like, it's best if you understand the mechanism, because you know how whenever I go over the mechanism, I always explained it step by step. What intermediate gets formed, like carbocation intermediate is flat and planar, so that's why it loses all stereochemistry. Or if we do a backside attack, we invert stereochemistry. Make sure to use terms like that when you explain the mechanism or explanation problem, right? So to practice that, whenever you guys do predicted product reactions or synthesis problems, each reaction you do, practice the mechanism if he gives it to you, and explain yourself like each step of the reaction, right? So make sure you really understand the mechanism.
I see, thank you.
Yeah, nice. Yeah, okay. And the yellow stars here are the ones that you should know for sure, like deeply, like about the mechanism, each step, each arrow, and each intermediate. Right. And all the reason why it's regioselectivity and stereoselectivity is like that. And here's a note card that I made previously. Front card, back card. Okay, so I'll end office hours here. I'll hopefully see you guys next week. And yeah, good night, guys.
Thank you. Good night.
Yeah. Good night.
Brian, what is study hall in your community?
Oh, study hall is exclusive to our OChem study session, where if you want more personalized direct support with less people, so I could like focus more attention and time on like you, then that's gonna be the one that is $99 for lifetime access. These free
Okay.
ones, Monday to Thursday, are like always gonna be free, 9 to 10 p.m. But if you want more like personalized direct support, then those are what the office hours are for. The study halls are for, the 2-hour ones.
Okay.
Yeah. Okay.
So bye.
Yeah. See you, everyone. Have a nice day.
Thank you.
Yeah.